All right, welcome back. Today, we're doing something a little different. We're going to pit 5 AI algorithms against each other in let's call it a gauntlet. Their mission is to sniff out cyber threats hidden in a massive pile of server logs. We're going to find out which one really is the best of the best. So, let's get into it.
So how do you do it? How do you actually find a cyber attack when it's buried in literally thousands of server files? I mean, think about it. It's like trying to hear one specific malicious whisper in a packed stadium where everyone is yelling. That's pretty much the daily reality for cybersecurity folks, except their stadium is just a mountain of digital data.
And when I say a mountain, I'm not kidding. Look at this number. For our experiment, the AIs have to dig through 2,741 separate server log files. Imagine trying to do that manually. It's basically impossible, right? But for a machine, that's just a warm-up. Okay, so before we just let these algorithms loose, we really need to get a handle on what they're actually dealing with. What does this digital haystack even look like? This jumble of text right here, that's just one single line from one of those thousands of files. It's a standard Apache server log. I mean, to you and me, it's mostly gibberish, right? But to a security system, every little piece of this is a potential clue. Is this just a normal visit to a website, or is it the first step of a major attack? Now, imagine millions of these lines. Yeah, you can start to see why you'd need an AI to have any hope of connecting the dots. So, you can't just dump all that messy, raw log data onto our AI models and hope for the best. It doesn't work that way. First, you gotta prep the data. It's kind of like a chef in a kitchen, right? You don't just throw whole vegetables in the pot. You've got to wash them, chop them, get them ready. We need to turn all this chaos into something clean, structured, something the AI can actually work with. And that prep work happens in 2 big steps. First, we parse the logs. That's just a fancy word for having a script go through and translate all that computer speak into a nice, neat table. Easy enough. But then comes the really cool part, what's called feature engineering. This is where the script starts calculating important stuff from that table, turning raw numbers into actual clues. And these clues are what our AI is going to use to go on the hunt.
And this is what I'm talking about. This is where the data really starts to become intelligence. We're not looking at weird log lines anymore. Now we're tracking real, concrete clues. Things like, how many times was this page requested? What percentage of those requests resulted in an error? How many different IP addresses are hitting this one page? See, a sudden spike in the error rate. That could be the telltale sign of someone trying to brute force a password. These are the kinds of fingerprints our models are looking for.
Okay, the data is clean, the clues are laid out, it is time. Let's get our contenders into the arena. It is time for the algorithm gauntlet. So, here they are, our 5 contenders. Now, the key thing to know about all of them is that they're unsupervised models, and that's really important. Think about what that means. We're not giving them a picture of a known hacker and saying, go find this person. No. Instead, it's like we're telling them, hey, just watch this server all day. Figure out what normal behavior looks like, and then you tell us if you see anything weird or out of place. They have to find the bad guys without ever being told what a bad guy looks like. So, how are we going to pick a winner here? It's not as simple as just seeing who finds the most weird stuff. That's not enough. For a security tool to be useful in the real world, it's got to be more than just accurate. It also has to be dependable, it has to be fast, and it can't hog all your computer's resources.
First on the checklist is stability. I mean, you need a model that's not, all over the place. If you run the same test 10 times, you expect to get pretty much the same answer 10 times. Imagine a security model that flags something as a major threat 1 minute and then completely ignores it the next. That's useless, isn't it? So high stability basically just means you can rely on it, you can trust it.
Okay, next up, performance. This is all about raw accuracy. How good is the model at telling the good guys and the bad guys apart? And we have a way to measure this, called a silhouette score. The best way to think about it is, imagine you're trying to draw a really clean, sharp line between what's normal traffic and what's suspicious. A high silhouette score means the model drew a super sharp line. No confusion, no overlap. A low score means the line is all blurry and messy. We're looking for that sharp line. All right, the tests are done. The numbers are crunched. We've checked their speed, their memory usage, their stability, their performance, everything. It's time to see how our contenders did.
Let's find out who won.
And right off the bat, we see something super common in computing, a trade-off. On one hand, you've got the SGD OneClassSVM model. This thing was an absolute speed demon. It was the fastest to train, which is fantastic if you need a system that can learn and adapt on the fly. But then, on the other hand, you have Isolation Forest. It wasn't the fastest, but it was incredibly light on its feet, barely using any memory. That makes it perfect for machines that don't have a ton of power to spare.
Okay, but speed and memory are one thing. What about pure performance? Let's look at that silhouette score, our measure of how sharp that line is between good and bad. And, yep, there's a clear winner. Isolation Forest gets the highest score by a good margin. It was the best at telling the difference between normal traffic and potential threats. No contest.
So, what does that mean in practice? What did our winner, Isolation Forest, actually find? Well, it flagged about 10% of all the traffic as being anomalous or suspicious. And this is actually fantastic news. See, when we set up the experiment, we basically gave it a hint, telling it to expect around 10% of the data to be weird. The fact that it landed almost exactly on that number shows it's really well-tuned. It's not being overly paranoid, but it's not missing stuff either. It's in that Goldilocks zone.
Speed is great. Performance is crucial. But a real champion has to be good at everything. So now, it's time for the final showdown. Let's look at the big picture and see how they all stack up against each other. And here it is, the final verdict, all in one chart. Now these spider charts can look a little weird, but they're super useful. Each point on the web is one of our tests: how fast it trains, how fast it predicts, how much memory it uses, and its performance. The bigger and more balanced the shape, the better the all-around model is. You can see how some models are really spiky in one direction, like they're amazing at speed but not much else. But look at Isolation Forest. It covers the most ground overall. It's got that perfect mix, great performance, low memory, and it's plenty fast. It is without a doubt the all-around champion of our gauntlet. But here's the most important takeaway from all of this. Even though Isolation Forest was our winner today, that doesn't mean it's the best algorithm for every single job out there. There's no magic bullet. The right tool always depends on the mission, right? If your number one priority is pure, raw speed, you might still go with that SGD model. But for this specific task, if you're looking for the best overall balance, yeah, Isolation Forest takes the crown.
And that kind of leaves us with one last big idea to chew on. This whole gauntlet approach, this idea of making a bunch of different AIs compete to see which one is best, it's not just for finding hackers. Think bigger. What if you use this to sift through financial data to find insider trading, or analyze medical records to spot the earliest signs of a disease, or even look at climate data to find patterns no one's seen before? It makes you wonder, right? What other secrets are hidden in the world's data, just waiting for the right champion algorithm to find them?